In this video, we're going to go over the paper called Pseudo Labels, which is a work by Google, published in CVPR 2021. Pseudo Labels is a semi-supervised learning method, and its key contribution is to improve the accuracy on the ImageNet large-scale visual recognition challenge to 90.2%, which is 1.6% better than the state-of-the-art. It is based on a teacher-student network, whereas in contrast to the works that use teacher and student networks, in this work there is a feedback mechanism that tells the teacher when it needs to generate better labels. The pseudo-labeling framework works as follows. There is going to be a teacher network and a student network. Unlabeled data will be assigned a pseudo-label using the teacher network, and then these images are going to be combined with the labeled ones to train the student network. So the use of pseudo-labels as well as regularization and data augmentation usually leads to a student network learning good representations. The challenge, however, is the problem of confirmation bias in pseudo-labeling, meaning that if the representations that the teacher network generates are inaccurate, the student will learn from inaccurate data, which degrades its performance. In this work, feedback mechanism has been used in order to let the teacher know when its pseudo-labels and how its pseudo-labels are affecting the student network. The feedback signal, which is the performance of the student on the labeled dataset, is going to act as a reward to train the teacher throughout the course of the student's learning. So this learning happens in parallel. The student uses the mini-batch of pseudo-labeled data to learn, and then the teacher learns from the reward signal of how well the student performed on that mini-batch of labeled data. In terms of data, they focused on ImageNet as labeled dataset and JFT300 as the unlabeled corpus. Two efficient networks have been used, one to act as a teacher and the other one as the student, using the pseudo-labels mechanism. And the resulting student network is going to achieve a top 1 accuracy of 90.2%, and also generalizes to ImageNet real test set. They also performed smaller scale semi-supervised learning experiments using resident models on CIFAR 10, SVH N1K, and ImageNet 10%, and again showed improvement associated with pseudo-labels. We can see this improvement on the top 1 accuracy of ImageNet and PrecisionNet 1 for ImageNet Real as well. Let's discuss the pseudo-labels part first. Pseudo-labels are going to be used in order to train the student model. This means that you're looking for a set of parameter values for a student model based on these pseudo-labels such that it minimizes this loss. T here is going to be a very well-trained teacher model, and the objective is that ultimately this student model that has been basically trained using the pseudo-labels be good, and this means that it exhibits a good performance on the labeled data, meaning that this loss becomes small. One thing to note here is the dependence of the parameters of the student network to the parameters of the teacher network, because the pseudo objectives or pseudo targets that are basically denoted as T of XU given the parameter set of theta T is what determines how we can get to the best student model parameters. This dependence can be utilized in order to write this. Denoting the ultimate student loss on labeled data. And this renders LL also a function of theta T. So you can write the optimization objective as this. So this time you want to minimize, using theta T, the ultimate loss of the student network on labeled data, where the parameters of the student model ultimately is a function of the parameters of the teacher model computed this way. The intuition behind the feedback mechanism in this work is that as you are training the student network and the performance of the student network goes high, it makes sense to adjust the pseudo labeling mechanism in order to lead to better benefits for the student model. And this is facilitated by the use of the feedback mechanism. Inspired by the meta-learning frameworks, and given that in this case the training of the teacher network happens on a meta level, the practical approximation that has been used for theta SPL given theta t is this. In this case, eta s is a learning rate. So you're using this approximation and then you plug it in and rewrite the LL loss with this new value, which you can call theta. Now in training this part, they first of all ignore, so this is a trick, they ignore the higher order dependency of theta s on theta t and assume that theta s is fixed. And in order to make this trainable, the outputs of, so basically the teacher model outputs a soft inference values. To train the student network, however, they sample hard labels from the distribution of the teacher network. And they mentioned that this is necessary for the larger scale experiments, and for the small scale experiments where the soft labeling can also be used, there hasn't been a significant gap between the performance measures of the two. All in all, you're going to have an alternating optimization scheme, which works as follows. In the first step, you get a batch of unlabeled data XU, use the teacher model on it, and then do one step of optimization to get this. This is the student model optimization part. Now you draw a batch of labeled data and you reuse the updated parameters of the student model to perform the optimization for the teacher model, namely this. Another way that the authors have utilized in order to better train the teacher model is by the use of auxiliary objective. To do so, they focus on the teacher model's training and augment it with a supervised learning and self-supervised learning additional objectives. The supervised objectives is simply using the labeled data for training. And the semi-supervised learning objective is based on unsupervised data augmentation. The student model here has only used pseudo labels, so one way to improve its accuracy is actually to fine-tune it on labeled data. This means that after training the student model using the pseudo labels, the final values of the parameter weights are going to be taken, and then the model is going to be fine-tuned on the labeled data, and the results indicate that the accuracy will be improved. The first section after this talks about the 2-moon experiment. For this, a 2-moon dataset has been generated with these specifications. So you have 2,000 examples forming 2 clusters with 1,000 examples. 6 examples are labeled, 3 examples for each cluster, and everything else remains unlabeled. The architecture they use is a feed-forward, fully connected neural network, 2 hidden layers, 8 units each, with sigmoid as a Snow linearity at each layer. They did not apply any regularization. The initialization of weights have been the uniform distribution between minus and plus 0.1, and everything was trained with a constant learning rate of 0.1 and a stochastic gradient descent. And the results indicate that the meta pseudo labels has a higher success rate. Looking at the figure 2, you can see the advantage of meta pseudo labels over pseudo labels and supervised as well. In this paragraph, you see the details of the configuration that they have used for these datasets. And the next paragraphs go over the models, which, for example, in these experiments, Resident 50 was used with 25.5 million parameters. They then compare the results of the meta-pseudo labels against methods with the same architecture. They do not compare against methods with too much larger architectures, and do not compare with the training procedures that include self-distillation or distillations from a larger teacher. And here's the reason why. Because larger architectures and distillation is potentially able to improve any method, possibly including this method itself. Here are the results, and as you can see, meta-pseudo labels exhibits a great performance. This page also goes over more implementational details. Namely, you have a batch size of 4096 for labeled images, and you have this batch size for unlabeled images, and some other important information. For the larger scale experiment, they have been using the efficient net L2, and with the same hyperparameters as noisy students, except they use this resolution instead of that. And the reason why goes back to this model parallelism, which requires a shape of 512 by 512. And the results of the meta-pseudo labels indicate that they are improving on the state-of-the-art on ImageNet. They have also presented a reduced meta-pseudo labels, which is a more economical model, or a light version, which obtains 86.9% top 1 accuracy on ImageNet, which is a pretty good accuracy.